Hello, everybody. We are back. I hope you had a great break. And we continue with Charlie Vartanian. He's going to talk about technology for diesel. Actually, the use reduction of diesel or the reduction of use of diesel in non-grid connected communities as essentially an interim solution to go to near zero carbon generation.
Perfect lead in, and this is also a nice building off of Professor Canicer's examples of renewable integration and how energy storage interacts to facilitate that. I'm going to show a couple examples of a midpoint where energy storage is used to hybridize diesel systems, not to replace them, but to optimize them to reduce the amount of diesel burned while we have diesels in the field. Also, I like the professor's last point on CapEx as a limitation. It'll always be a limitation. But I'm here from the government, and I'm from the government, and I'm here to help. The famous Reagan quote, the famous 9 words. Here's a tip for those looking for funding. The Department of Energy, U.S. Department of Energy's Energy Storage Grand Challenge. If you search on that, there'll be significant funding opportunities, both for the study side. We'll look at what is an evolutionary path. Now the focus is on energy storage and how will that be brought to bear to solve some of the solutions discussed today. I'm Charlie Vartanian. I'm dual-hatted. First, I do want to thank Professor Grass and the FTC SUSTEC initiative for organizing the workshop. Also want to thank Professor Lucan and your initiative is longer. Planet Positive 2030 initiative, and that's sponsored out of the IEEE Standards Association, and that's the hat I'm wearing. I'm here as an IEEE Standards Committee 21 volunteer for over 20 years working on the IEEE 1547 standard. So with my remaining 27 minutes, my goal is to show how standards can foster the implementation of innovative technologies, the technologies, getting them connected to the grid safely, reliably, and then releasing them to perform new and novel applications. With that in mind, it does start off, we can go to the next slide. Oh, I'm in control. Yeah. Yes. I'm not speaking for the IEEE. These are my points. Any errors or omissions are all mine. And this is also the work product of many volunteers, including Bob Sykes there, who will present tomorrow, and is my backup. If there are any hard questions in IEEE 1547, Bob
I may or may not know what the answer is.
I bet you will. Also, Bob is a working engineer from this community, so he can put a lot of the standards discussion in local context. Which direction should I point? Doesn't matter. I broke it. No, outline. So I do want to touch on first 20 slides. I'm going to try to hit in 5 minutes. The Standards Committee 21 focuses on 2 standard sets. 1547 addresses interconnection of distributed energy resources with power system, essentially with utility. Whatever your local utility is, they are likely using 1547 to set the minimum performance requirements. That's interconnection. The other set of standards is 2030, and that's interoperability. Now, Professor Lucan kindly sent me some high-level slides on standards development, and we've always were driven first by safety and reliability, more recently on interoperability and integration, but at a higher level, strategic level, she shared some information. Standards Association now wants to go from interoperability to impact. What is the end effect to address issues like climate change? So from a standards development standpoint, that really brings a different facet to keep in mind. It's a facet that, I'll have to change my thinking. But I could see the appeal of that. Here's I want to touch on that 4 years. It takes 4 years to develop a new standard. The pace of technical change and the technical challenges really can't be accommodated with this 4-year cycle. So really a call to arms for the younger engineers, get involved with standards development and bring capabilities like data science. I'm always amazed how data science can impact, influence, and affect real solutions much quicker than some traditional methods. But this is the project that the standards, SC21 sponsors projects that go through this process to develop, get approved, and publish standards. The 1547 standard is very successful. It's the standard itself, and it has a number of guides. So the standard is a shall, you shall meet this requirement. The guides are, you may, recommended practices, or you should. So they give us a guidance on how you meet the shall standard. Here's an important point. IEEE 1547 addresses distribution. There's a newer IEEE standard sponsored by PES. That society, Power and Energy Society, that's written a similar standard that's now applied to transmission. What's good is there's tight alignment, 95% consistency in terms of the requirements, with the adjusted needed for the respective frame. This isn't an I-1547 seminar, so for those who need to work with it, the slides are going to be available to registrants. So if you're really interested in 1547, you can go back and then there's some references. But a big change in 2018, so the blue language was what's changed from 2003 to 2018. A big one was including interoperability requirements. That's how does the device communicate with the local utility, what language it uses, and what are the minimum information exchange. And back to one of Bill's points on systems that can't island. In right before this was published, Hurricane Sandy hit, and all these PV panels in New Jersey and along the eastern seaboard, people were frustrated and complained to the local governments that I can't get my solar panel to work, my utility can't tell me. It's because they were compliant with IEEE 1547, which baseline requirement is if the local grid is out, you can't backfeed that grid unless you're isolated. So there was no way to make all these standard compliant devices carry load. You need a certain amount of infrastructure in place to isolate yourself. And then you need a grid forming inverter. And most PV inverters are grid following. They just inject current against a stable AC waveform. Now, you in Alaska already have a lot of experience with grid forming inverters, but I'm always amazed. It's a hot topic now among, I'll call, well network systems that haven't needed it, act as if grid forming is new. Oh my goodness. No, you've had grid forming inverters. Bob, here, since inverters were probably first deployed, they've needed to be grid forming up here. UL 1741 standard is an important thing. That's how you certify that device. So if an inverter is listed UL 1741, then it's been certified by UL and tested by an NERDL that it's compliant. And that's an important point in terms of standards development. Once it's published, it's really great to a way to have conformance and compliance. And one way is to have UL certification. So that UL 1741 is a certification to verify that a listed device is compliant with IEEE 1547. Clause 8, islanding. That's a hot topic for isolated systems. We're going to go talk about 2 islanded systems. But I'm going to jump ahead. Let's see, again, some of the details. And again, I'm here sponsored by the Department of Energy, Office of Electricity Energy Storage Program. My mission is to help close gaps in standards to further facilitate the adoption of energy storage. Why is it important to get standards in place or update existing standards? Without the 2018 update, Blackstar would be out of compliance in some implementations with the standard, the original 2003. Forming microgrids could be out of compliance, doing active bar and voltage sag, voltage support. So this is in part a big driver. This was me speaking to the California Public Utilities Commission in 2013 saying their multi-billion-dollar initiative to incent energy storage in California would have a major barrier if we didn't get the 1547 standard upgraded. And to their credit, the California PUC had their Rule 21 working groups get involved and make sure that they supported getting these rules changed. So, you know, the worst case is when a standard really hampers innovation. I mean, a standard is there for minimum, it's not there for innovation. You're here for innovation. The standards are kind of the baseline protective rules of the road to follow. Again, the worst case I've seen is when that's unintentional, inadvertent barrier to do something innovative, just because no one thought of it when writing the standard. And you all are going to run into that. So if you're involved in standards development, you can be part of the solution when you run into that. This was accomplished. This range of energy storage applications can be done with any 1547-2018 UL 1741 SB certified inverter, similar to New Jersey. If you have a 1547-2003 UL 1741 non-appended inverter, you can't do some of this. While I'm on California, really like the firewall presentation. One item, Michael, you know what Blackstart is, but you're also using data science. Impressive. But for Mohammed and that team, the California PUC has an open investigation on public safety power shutoff. So if you search on public safety power shutoff, California PUC, there's a really robust website that's taken all the input from the fire safety people, everyone in terms of how can they better manage. Right now, it's a blunt tool is the utilities will shut off whole areas during high wind. And that's getting more and more prevalent. Getting input from Oregon, for example, looking at the same thing. But there are also some really innovative solutions being discussed of how you can use microgrids to offset the impact. That was one item I wanted to share with your team. Bob can answer 1547 questions for the remainder of today and tomorrow from an Alaska perspective. But if you want to get into the minutia of some of the details of especially the energy storage interconnection standard, Mike Ropp of Sandia National Lab was the chair of that effort. And he's actually chair of a new working group, 1547.4, which is a guide to interconnecting microgrids in a 1547 level.
And then 1547.9 just started.
Well, there you go.
Landed just in.
Bob just volunteered to answer any questions on energy storage interconnection. Thank you. And Bob, you're presenting tomorrow, but it was on like monitoring or measurement?
It's on, yeah, it's on monitoring. I have a background in monitoring too.
Well, maybe multidisciplinary is a way of engineering up here.
What?
I spent 20 years at SoCal Edison. That your cube was about what you did and where you did it was tightly. You do this and you don't step outside the bounds. I guess you don't have that luxury, maybe in Alaska. In the last, one's an old project, more recently, and another thank you goes out to the Alaska Center for Energy and Power at University of Alaska Fairbanks campus. I saw an ASAP sticker on someone's computer. They did a lot of the analytic grunt work behind Cordova Electric Co-op's. The reason for the battery energy storage is successful deployment, and what I've been doing more recently, figuring out ways how do we build on this device. It's been out in the field and reducing diesel fuel usage. And then I'll touch on an old project I promoted technically and got approved, which was a battery energy storage on Catalina. Now, both of these are examples of hybridizing the diesel system. So the battery energy storages aren't doing any of the traditional use cases. They're not integrating renewables by shifting or shaping, smoothing output. They're not doing peak shaving or load service. These two batteries are interacting with the diesel, the utilities diesel plant, basically to optimize the resource operation, but the ultimate goal of reducing fuel. And in both cases, very successful. If you're from Alaska, you probably know where and what Cordova is as a community. But it's also a wonderful test platform for testing new and novel ideas, in part because they have a very technically strong leader and their CEO, Clay Copeland, if you've worked with him. And then, you know, the folks who support him, like the engineers and managers out of ASAP. But They're a hydro-dominated system that runs diesel. So what they had been doing is actually getting frequency control over to the hydro units, and they were fluttering these butterfly valves, manual frequency. Well, that's a lost opportunity. That could have otherwise been producing energy versus having some water bypass for frequency control. So they put out a battery, made a pitch with ASEP to put a battery essentially to take over frequency control and release the hydro to as much energy, as much, water that we converted to energy. That was a simple goal, stage one. It worked. 1 year recorded, 50,000 gallons of diesel fuel reduced. Again, this is a great example of, I think, a practice could be implemented cost effectively. In this case, supported through DOE funding. DOE helped pay for the battery energy storage system to get access to and evaluate this application. It worked well, but the battery would have paid for itself in a couple of years just on the diesel fuel use reduction. And it was a lithium-ion battery system sold by ABB with a SAF battery inside. The same SAF battery team that did the Golden Valley Electric nickel cadmium years ago. There's a picture of the battery, and it's amazing. It's 2 containers. One is the lithium-ion batteries. The other is a 1 MVA ABB inverter set that can switch from grid following to grid forming. It is an isochronous mode. It is setting the frequency when it's in operation for that whole item. It allows anything else connected is following the heartbeat set by this battery. And what's good is you can set it up for basically continuous charge and discharge. Set though, if you want it in that role, it could be on all the time. In this case, releasing the hydro to maximize energy output. Last project I did, I can't hold a job. I worked for PNNL for about 5 years, but one of my real focuses was to get some money to clay into ASA to take the battery and let's find the next application. Now here's where multidiscipline comes to play. The scenarios at Cordova Community Medical Center is, I would argue, they're critical load. So how do we hotline the battery during an outage? So we're working with them to come up with a basically system reconfiguration scheme such that the battery and a single diesel can be isolated from the rest of the outage system and hotline. But an interesting one that we added to that is, well, what's the maximum electrical service such that they can max out the thermal air stored within the envelope of the building ahead of a known storm. So they got that all maxed out. So there are folks right now doing basically a deliverability study to say, what's the maximum energy, we can transmit to the distribution system without overloading a circuit or violating the bus voltage, and pre-charge and include thermal storage along with electrical storage to help mitigate outage. Now I really hope that goes forward. The micro PMUs mean this is highly wired, so we can see granular detail of how the electrical system is performing when given these new challenges. Energy storage isn't new. One of my first assignments at SoCal Edison in the late 80s is I was a custodian of the Chino battery energy storage system dynamic stability model. You know why? I was a new guy and no one wanted that turd in their inbox, so I got it. But that was my first exposure to grid connected energy storage. And that really just sort of set the whole direction of my career, was being the custodian of the Chino battery model. Well, the same people and that's a picture of the Chino battery up there, 10 megawatt lead acid system. It had a dynamic damping that could self-detect subsynchronous resonance and start damping the system. And we showed at SoCal Edison, if that battery had been 200 megawatts, in 1996, it would have, that was all the damping capacity that would have prevented the 1996 underdamped event that took the whole West Coast down. So that was another one that still motivates me today, the power of correctly applied energy storage. A small amount can have a big impact. In that case, it was a NAS battery. Now in this circumstance, Oh, emissions mitigation, the diesel plants were violating California emissions requirements and was booking a bunch of violations. So they were gonna put a $60 million undersea sub-transmission cable. And I take credit for saying, well, wait a minute, I've heard about this energy storage stuff, what if we put a battery? And it just, again, hybridized the diesel, so the diesel stay in there optimized in a more efficient band. Could we meet the emission compliance? Short answer is yes. And it's been on for a while, so 2017, that was, I think, the 5 year. It had been on 5 years, 2012. Been in continuous operation, reducing emissions output, and that was the reason, but fuel reduction was not a driver or purpose. Last time I checked, they don't even bother counting the fuel savings. But I did a nice back of the envelope. Here's a discussion describing more detail how, keeping the diesel in a better operating bandwidth helps them meet their emissions reduction target. I took the liberty of finding some generic information on what's the diesel use, gallon per hour at a certain power point. When you're low loaded, low efficient versus high efficient. And hey, similar size system to Clay's. And I say that'd be about 2 megawatt peak average on Catalina, 1 megawatt or less off peak. Just running this scenario, a real back of the envelope, 60,000 gallons a year reduced. Using sort of this proxy generic information. So it gave me confidence that I'm not an order of magnitude different from a similar application where Clay is just using that storage to make sure other assets are in their optimal operating condition. How am I doing time-wise? Do I have 3 minutes left?
Yep, we've got a few minutes.
Again, I think moving us to that, the ultimate goals of minimizing or reducing carbon from our energy supply and distribution system. This is the middle ground. Hybridizing diesel. There are folks here, Kodiak in Alaska is one example of a great battery wind diesel system. They'll be presenting at the IEEE PES general meeting in Seattle, July 22nd, the Monday, 1 to 3 p.m. If you're going, look for the Regional Clean Energy Projects and Programs session. I'll be chairing that. Kodiak will be speaking there about more. And I think this is where people really see energy storage. I do think that's the effort and the focus is rightly placed on that. Working with energy storage to integrate renewables. And so I'm not talking about that here. Prior professor did a good job showing energy storage and other options like variable speed generators. I'm a fan of variable speed pump storage, for example, that had not been available 10 years ago. It's available now. So I think variable speed pump storage is another form of variable speed generation that next generation of engineers will take advantage of. These links hopefully work in the PDF version you'll have access to. If they don't, and you have any questions or want the right links or just the documents, feel free to email me. Thank you.
Thank you very much, Charlie. So we do have a bit of time before lunch, and are we planning for lunch too for 12 o'clock or?
Yes, it will be delivered here.
Okay. So we will have time to talk until lunch
Right,
arrives,
for 30 minutes.
about 12 o'clock. And you have your question, the first one?
I do. I have a question.
So I also invite, of course, people online to pose questions, and we might have some in the chat, so we will double check that. And of course, also invite Claudio to respond to questions. So let's see how this is going to work.
So my question is
And
on,
maybe the Mohammed team has to find Mohammed.
Yeah, we'd have to see your design presentation, so.
Ah,
I believe
okay.
he's down there.
So you will speak for Mohammed. Okay, perfect.
so my question's on energy storage systems, batteries in particular. So it probably would be addressed by you, maybe have some information on that. So speak a little loud. So there's another alternative solution for energy storage, and it's super caps instead of batteries. And there's advantages to both, and then there's also a hybrid solution where you take the advantages of capacitors being, the ability to provide energy very quickly. And then you use the batteries to do the sustained piece, like those hybrid solutions. I don't particularly like supercaps because of the electrolyte in there. It's a little bit dangerous, especially in the home. But there are supercaps that are available that could be built using solid state instead of electric. So you can use alternating NP layers with the thin dielectric and create a very, very lightweight and high efficient supercap. I'm just wondering, do you know anything about the adoption of those in the US?
I'll start. So Maxwell has a super cap product. And they actually have a package, so the voltages mimic lithium-ion batteries at the cap levels. You can build them up in similar strings and use the same inverters. I do think then here's the issue with their short discharge duration. They're great at dynamic dampers, kind of like these shock absorbers for the grid.
Yeah.
And there was a successful shock absorber using earlier generation capacitors in Hawaii. But that being said, there's such a focus on extending the duration of energy storage, so I think that leaves the capacitors out of a lot of the current, I'll say it, policy and DOE level storage. But Maxwell is making progress, and I do think there's an opportunity to use them at large scale as bulk power system damping systems. Now, if they improve the packaging, it'd be interesting to see other implementations maybe that are more amenable to grid edge, closer to the load. And I like the old idea, there's a hybrid battery proponents, more in the automotive realm. I was seeing that pitched more for automotive EV application. And a question back to you. Do you know why that is old? It sounds like you know quite a bit about caps, but my recollection was the hybrid system with the lithium ion capacitor combination. There was some traction for a while in the EV community, and then that faded.
I don't know why it fizzled. Maybe it's just the volume, the area and the required to put the two of them together. I don't know that for sure, though. Capacitors, so for people that don't, probably everybody here knows, but capacitors, if you implement those as your storage mechanism, they have a lot of advantages. Probably the biggest advantage is you have infinite charge recharge cycles. They won't wear out like a battery. The disadvantage is as they discharge, you need a voltage regulator on the output. Otherwise, you're going to have a very unstable voltage system.
And the voltage begins discharging as soon as the voltage drops as soon as it starts discharging.
Yeah, so you need a regulator on the other side. You don't need that on batteries. Batteries, the way they store with chemical reaction, they'll hold voltage, but they have limited charge reset.
For the EEs, you'll remember that asymptotic curve of a capacitor, that the instantaneous current is infinite when you short it.
Yeah. So in the idea of a system that needs a lot of current, instantaneously, that hybrid solution makes a lot of sense.
If I may,
I'm on a well, so it would be nice to have that capacitor system to supply, the instantaneous current of a 2 horsepower well.
Another perspective from online.
Yeah, Claudio is.
excuse me, if I may, because this is becoming a personal discussion, but I just wanted to add that the example I presented of the VSG, the variable speed generator, is designed to have in the DC link a supercapacitor, and they have actually implemented it that way, which provided the fast response of the system when the generator couldn't respond for integration of renewables, and the objective was to behave like a flywheel, so very fast response when the generator wasn't able to respond, and they have demonstrated this in this particular system that facilitates the integration, especially of wind power in microgrids.
Okay.
So also to jump in on what you just mentioned with flywheel, Charlie mentioned Kodiak. So Kodiak, Alaska, for those that don't know, it's an islanded microgrid here in Alaska. They had an issue a few years ago where they installed a new crane at their dock. They're a very large fish processing. It's like the main thing that happens in Kodiak. So the issue was that they put in a new crane much larger than the old crane that was there. And what they were finding was that they would kick the crane on, and their frequency on their grid, I mean, they were seeing dips all the way to like, I think 56, 57 hertz, like just instantly, right? They'd go to pick up a container and the grid frequency would just drop off the cliff. And then subsequently, when they went to go lower that container back down, that crane utilizes regenerative braking almost as its brake to allow the container to go back down. So they did a solution that involved flywheel storage with GE, I believe. And then so they installed some flywheels to basically soak up that load because they're a good sort of middle ground between capacitors and batteries in that they can stabilize your grid pretty effectively. I believe since then they haven't had really any issues. The main thing with Kodiak is that they run, I think, 98 or 99% renewable. They have a large dam and then they have large wind also there in Kodiak. So, and then also to mention to you, everybody that flew in, you guys all probably flew over Fire Island and you probably saw wind turbines we have out there. Chugach Electric, our largest company around here, they just installed 14 Tesla Megapacks here in Anchorage to do, I believe, to better utilize their wind generation capability.
They also have a flywheel
Here in
down at
Anchorage.
their yard. They put in a battery and a flywheel. What was the ABB's in?
Yeah, and well,
And
Mike,
they put them in just so they could see how they could figure out how to use them. The advantage of the flywheel with the batteries is it saves the battery from taking hits. That would decrease the life of the battery significantly. It saves a million hits a day or something like that with the.
same
with the
logic
flywheel.
on automotive was taking acceleration, handing it to the extended the battery life
Tremendous.
significantly, taking that shock, initial shock away. Vicon is a company that's actually integrated flywheels with the cranes themselves, and they've been deployed on the mainland in a couple spots. If they're selling through GE, that'd be a real big plus for Vicon, but what's clean on that, it's integrated right with the crane, the freight crane.
So what I'm hearing is, by bringing significant, but still small battery storage into the diesel-powered quote-unquote communities, we can, in the interim, reduce fuel needs, period.
And as you get more renewables and maybe the use case shifts to renewable integration, what's great is, when the sun's not shining, you have that excess capacity, you can lean more on those other sort of back to the scene. Yes, short answer is yes, you can
so
deploy
that
them
very-
today.
So that very same battery supports the transition.
Yeah, it supports it.
So question from my side is, you mentioned that the cost of the investment was essentially at an ROI of 2 years, solely in the savings of diesel. So what is the lifetime of these batteries? Like if I want to plan over the long range, when do I have to plan for replacement?
The lithium ion integrators are getting better. They're doing 20-year contracts where they're planning the replacement or addition. And they'll price that in upfront. So I'd say people can do a 20-year contract, but lithium ion, I'm most familiar with, they're pretty well versed on that. But the actual lifetime of the battery, depending on the cycle, is still 5 to 10 years. But so is the power electronics. I mean, inverters have even as checkered a reputation at this point. So there's going to be CapEx replacement for the utilities. Capitalized maintenance is an investment opportunity. I don't know if there are any up here investing in utilities, but it's like nuclear. I think there's a match. What the utility industry did with nuclear fuel investment, so it can be done similar with battery replacement. Sort of programize it.
The other question I had was, as we are bringing the technology into the remote communities, how do we handle maintenance? Like what is there in terms of technically trained personnel that,
Being in Alaska,
If I may,
okay, go ahead, Claudio. I
yeah,
know that,
this is a very good question because this is one of the major challenges, in fact, for integration of or changes in the energy systems in these communities. You need technical expertise. And that's one of the parts, that's one of the issues that need to be considered in all of this. It's not just equipment, deployment costs, but also technical expertise. And there are programs that are being, at least in Canada, being funded through NRCan for training on personnel locally. And it's an important question and needs to be addressed. As the same, you need to address the equipment deployment and planning. All of those is part of it. It's part of the solution. Needs to be addressed.
So another aspect of that complex is the recycling of materials. I don't know how they're, what's in the master scheme of the battery piece, recycling the lithium, for example, maybe some of the electrode materials. I see there's a lot of mom and pop shops popping up to do this in the automotive industry, which is kind of very eclectic and a non-traditional way of doing it, and maybe a little bit scary, so to speak. I don't know what's going to happen on the commercial side. You have these large scale battery packs. What the plan is to recycle the raw materials.
Right now, I know people are paying at end of life to have the batteries removed, and they're basically being warehoused because there is no commercial infrastructure yet. Tourist cycle scale, it's solid waste management. Again, and actually it ties into the bigger picture. I do like a higher level view of these initiatives. Yeah, that end of life management. And environmental and cost impact.
So if I may, so Europe is taking a lead on a lot of those policy discussions. And I got corrected when I was at a meeting in Austria a few months ago, talking about these issues. And I said, it's not end of life, it's end of use. The material is not at its end of life. We are just at the end of use of a particular widget, of a particular item. And we now have to look at how we can take the materials in this widget and return it, if necessary, back to its molecular level to use it at feedstock for the next widget. So I've been corrected to use end of use, not end of life.
So that takes
Well,
energy.
Pardon?
That takes energy.
Of course, it takes energy, but we're living in an environment of limited resources. Like people are sounding the alarm bells about running out of copper in 50 years. Copper is, essential for many of our applications, but also is the preferred material to encase nuclear waste. Like the high level, like nuclear waste and for permanent storage. So that will take quite a bit of copper if that's what we are going to do. So the looking at properly reusing materials at the end of use, it will take energy, yes, but we have to do it if we want to have resources 500 years from now, or in the case of copper, 50 years from now. So it's a proper thing to do. It's not an idealistic vision. It is just a longer term vision rather than a short term vision.
Or the reuse first, right? The reuse.
Well, you can reuse it first, but
Couple chats have popped up.
so end of current
There
use.
might be questions.
Yeah, for the battery, we also talk about especially from the EV to the station battery, the second life of the battery. So this is and then after that, yeah, as Mikey mentioned, then you try to recycle the material. And the recycle has the two approach. That one is to recondition the equipment. So instead of scrap it, you basically pull out the equipment that you can recondition it and use it. The other side is okay, you scrap it and extract the material. So this is basically it's an ongoing research going, and then it's pretty active over there. And then also talk about the battery, even that we listened to that South Australia, Tesla put in the battery. Actually, by itself, it's a mixed performance because you try to use the one with the fast charge to catch the fast response of the system, and then some follow up. So the response, like Bill mentioned, that it's a hybrid system. Okay, supercap has a very high power density but low energy density. So you try to mix match the different device and then try to create a smooth transition. Okay, and then also during that, we see that some of the chat, they talk about the battery for this, the basically for the more short term, because there's some shell life, some shell leakage. And then the H2, that the hydrogen or ammonia, okay, that can be another option. And then from the Alaska point of view, because the hydrogen liquefaction point is the 253 degrees C. Ammonia is -33. So maybe ammonia will be a good option here because in the winter time, you're going to have a cold weather. So your cryogenic system can be minimized.
If I may add to what we just said about ammonia, that's a very interesting question we are trying to address with this project with DOE. What is the role of ammonia is going to play in all of this? There are other issues with ammonia which are environmental as well that one has to be concerned about. But however, ammonia is also another mechanism for storage in hydrogen without compression. So that's something that needs to be looked at, and we are planning to do so.
Yeah,
Okay.
of course, the ammonia, if you look at the thermal contents, ammonia is about 1/6 of the hydrogen by weight. So this is another issue that for the transportation, that storage, then you have to, there's no silver bullet. So we have to look at a different environment, different condition, and how can we utilize?
How do you utilize the nitrogen?
Yeah, but ammonia, because it's an NH3. So when you burn it, you're going to have a NOx.
Yeah.
So then that requires some capture also.
Yeah.
So that is the basic hydrogen, yes, that.
Mike, I did want to respond to one of the comments
Yeah, I
on
was actually gonna, which one were you gonna respond to?
the major increase in cost and
Yeah,
investment,
go ahead,
the
yeah.
cost. So, back to promote the Department of Energy Storage Grand Challenge has a goal of in 10 years, having 10-hour discharge duration at $100 per kilowatt at 5 cents per kilowatt hour per cycle used. Now, 5 cents per kilowatt hour, if you get your PV at 2 cents, you're down at a very low per kilowatt hour cost. That being said, lithium ion had a 20-year development time from invention to why, I'll say cost and performance warranted commercial production. So the U.S. Department of Energy is hoping that the next generation of technologies could speed that up and do it in 10 years. But that's a major constraint. And then I think a big debate in the industry on energy storage is, well, what's long duration? So DOE has said 10 hours as a start, but you talk about crew resilience backup, extended outage. Yeah, is 10 hours enough? It's very, in my mind, project or location specific. But if you have abundant wind and PV, if you have 10 hours of discharge, you have a lot more to work with. So you're gonna have fewer corner cases where you run out. But again, if you're interested in energy storage, I do think it's a good central location for the best thinking on how do we get to this long discharge, low cost. And it's likely to be something that follows lithium ion, like sodium. Or hydrogen has been added to that the scope, Professor. That was a good adjustment to that. I think hydrogen is in the mix.
For Alaska, I've been advocating multiple months for energy storage.
That'd be 20-year target. That energy storage super grand challenge. I'll take that to DOE and tell them how
Pump hydro works so well.
Well, pump hydro, you're going to have a evaporation, water evaporation that if you store over there, that.
One thing to think about here in Alaska, we get so much sunlight in the summer, right? Like a lot of Alaska is just amazing amounts of sunlight. So where we say, months long storage, in the winter when we don't get hardly any sunlight, that's something that we use.
I've been advocating June to January storage. I've been advocating that for the last 8 years.
Well, so let me ask another question here. Glenn, online, you posed a question about e-fuels. Would you want to comment on that? See whether we can get Glenn on, and then I see Prasad has his hand up. Glenn?
Hello.
Okay. There we go. Yeah, go ahead.
Yeah, so I was just thinking that fuels that are more normalized to diesel fuel that we can create. I've seen some other research using biology to create it with sunlight, and they're claiming close to 80% efficiency, which is, very large. Granted, it can only be used in the summertime, but you can always store it, and it's very easy to store. It's just like fuel systems we already know of. I guess the biggest challenge on those is trying to capture enough carbon dioxide to make the reaction work. And of course, it's going to take a 10-year thing on genetics to do bacteria solutions. I mean, that's how the old world did it, right? I mean, they ate up all the carbon dioxide, almost extinctified itself billions of years ago. And so, there's some real efficiencies that could be seen there. I understand it's a long-term solution. It's not a short-term solution for what we're talking here, but it's well worth investigating.
Well, thank you very much. And would you mind, if you have, posting a couple of sources in the chat, then maybe people can follow up later?
Okay, I'll look for them.
That would be
Thank you.
fantastic. We'll go to Prasad. I do see a hand up,
Yeah, Prasad. Where?
and you are unmuted, so we should hear you.
More of a comment than a question. I was just reading an IEEE article about nanoflow batteries.
Oh, please, he's here. Okay. Prasad, go
Hello.
ahead.
Dear. Hello.
Yeah, we hear you.
Okay. Yeah. Good morning, everybody. Yeah, it's a pretty interesting conversation regarding the applications of the battery energy storage, and especially for as one of the presenters, they mentioned about the long duration. My comment is about the challenge the utilities are facing is how to get the batteries back up to the power once they're discharged for a long duration. And I think, in fact, I would be very much kind of curious to know for the Arctic regions, like what are the alternative sources of energy we are trying to get the batteries back to the capacity, so that they can be providing the power for the next cycle.
Anybody would like to comment?
One quick comment.
Nope, he's done.
The current technologies have pretty much one-to-one charge to discharge time power ratio. Well, but the next generation of long duration, 10 hours and definitely above, will have asymmetrical charge and discharge time durations. So I think in the near term, it's manageable from a project scoping and planning. Safe to assume for initial cut, you're going to get just the only extended time in recharging a lithium-ion battery is the loss makeup. So if you're 10% efficiency, you're going to have 10% more time to recharge after you fully discharge. And they really don't need a rest or recovery time on the modern batteries being put out today. But the next generation of long duration, those that'll go 10 hours, multiple days, that'll be a really good, something for the battery scientists to really work on.
Yeah, and also on the BMS side, you can basically look at the battery management system, and based on your load, and the load profile, and you basically plan for your battery storage. And of course, it really depends on sometimes if you have some surplus in your system, then that would be the charging time. So it's basically, it's a cost benefit point of view, because that also you look at the state of charge of the battery, and then you do the management. So this is the kind of management, the power management issue.
That's a really good point. So sort of opportunistic charging over time for some future emergency.
So you look at SOC, you look at the price of the electricity, especially if it's a deregulated market, price of electricity is very, it's a variable. It's a time and location dependent.
If I may, to add to this, because in the remote communities, electricity prices is not an issue. is the issue of reducing cost overall and integrating renewables. That's the main driving force. And also you gotta consider the fact that you gotta deploy this in a very remote, extreme weather conditions. So that's another challenge and that needs to be considered in all of this. Temperature management is an issue in these communities regarding energy storage, battery energy storage in particular. So that's something.
Yes, yes,
We need
Professor
to choose
Canizares, I
batteries
think
for-
you addressed the question rightly because especially with the extreme weather conditions, actually I live in Sudbury, which is the northern part of the Ontario. And we do have problems here with the batteries. They discharge pretty fast if the temperature goes below minus 30 degrees or minus 25 degrees. And in that case, bringing the batteries up to, again, their percentage SOC, like which is above 88%, like it's a big challenge for us to bring them to the capacity so that they can be good for discharging for the next cycle. And that's actually I was wondering, the alternative source for like a continuous source in that case, like will that be a reliability point of view, like a challenge, right? And that's actually that even the extreme weather conditions, they deteriorate the capacity of the batteries over the period of, let's say, 2 or 4 years. Because we got a set of like 500 kilowatt hour batteries, they discharge we had to replace them just in 2.5 years. I wonder like if there's such any other updates by the group here.
As I mentioned, in the process of installing batteries in remote communities, especially extreme north, you gotta consider the thermal management of these devices. And for example, one of the solutions that has been considered is installing or putting the batteries next to the generators to use the exhaust heat from the generators to help manage the temperature in these batteries. But that's something needs to be considered when deploying these batteries.
I think that's a good idea. Yeah, because for us, it was like a 28 kilowatt of the continuous heating provided for the batteries to keep them in like the ambient temperature. So I think that keeping them close to generator definitely it's a good idea. Thank you, Dr. Canizares.
A secondary challenge to the technology of remote is getting a strong commercial partner. A problem with a lot of battery integrators today is they're early stage companies with a lot of backup. And I know 2 really cratered projects in Alaska because they were too small and underfunded and understaffed to support it. Those of you who are around long enough may remember the Kotzebue flow battery. And I'd say that disaster was driven in large part by a startup company biting off more than it could chew. Thinking of the problem too.
Nolan had a comment.
Yeah, you mentioned flow batteries. So there is an article on IEEE Spectrum about flow batteries where the fluids have nano particles in there. And they're the ones that store the different oxidative states between the analyte and the catholyte. And they can achieve energy densities, according to the report, there's a company in, I want to say Chicago, that's worked on this for DARPA. And I just got an error trying to open the page to get a little more specific. But they say they've got like on the order of like 350 watt hours per liter of energy storage density, which is it's pretty on par with where lithiums are at today, maybe just slightly below the high end lithiums. And this is a more or less a recent development, but it's in progress. The technology is going to get there. It's just a question of are we willing to be patient enough to transition in a sane way as opposed to a haphazard and panicked way. So, optimism, right? That's kind of what I'm trying to get at there. But yeah, that's an actual IEEE Spectrum article. If anyone's interested to look at nanoflow battery.
We'll try to post a link, because some of the articles are available like directly from the website. So. And yes, flow batteries were discussed a lot around 2007-8. And actually, like I come from the Sarnia area, and we were actually looking at it and say, okay, if we want to do this, we could actually, as refining becomes less in the long run, we could actually use some of those big tanks and reuse the asset for flow battery, for the liquid storage, and so on. So one of the things that has been coming up in the discussions of energy transition is how do we reuse assets? Or are there ways of reusing at least parts of the asset? But another question that did not come up at all this morning is, what about geothermal as a source, not just wind and solar and potentially e-fuels, but there's geothermal for power generation and for heat, of course. And what about small modular reactors? Any
Yes.
comments? Should we keep these?
If I may address some of these issues, because geothermal in some of these communities, especially in the north, you have a soil issue and permafrost, and digging through that is a challenge. And even district heating is a challenge because of the issue that you cannot really excavate much. In part because it's difficult, and in part because it's costly as well. So that's something that needs to keep in mind. As geothermal is very specific to certain areas. So for those areas works, but in general, as a general solution, is a challenge, and I don't believe that's been looked into in a lot of detail, but people are thinking about how to integrate geothermal in all of this.
So maybe we can, seeing as lunch is ready for us, and I hope everybody else is online has a chance to take a break as well. Maybe we can include the discussion on the small reactors, small modular reactors in the afternoon discussion. Okay, so we are going to take a break now. And thank you very much for all your contributions, your discussion. We'll turn the sound off, and we'll be back at 1 p.m. Alaskan time, sharp, with the next presentation. So see you then. Thank you.